So welcome all of you to the 5th lecture on gravitation. So far what we have done is to analyze how to determine large distances, how to determine the periods, and we also discussed at great length the 3 laws that were formulated by Kepler based on observations by astronomers, especially those of Copernicus and Tycho Brahe. The great thing that Kepler realized was that a very simple description of planetary orbits could be obtained by shifting the center of the orbit from the sun to that, from the earth to that of the sun. Of course, these orbits were not completely circular. They were elliptical, which we will ignore to a large extent in this course. But you should know that Newton's formulation of law of gravitation naturally accommodates the Keplerian orbits, the so-called elliptical orbits. In fact, the most general Keplerian orbits are elliptical if the orbit is bound. Otherwise, it can be elliptical and also parabolic or hyperbolic, the so-called conic sections, which you are either studying or which you will study in your 12th standard geometry. So all these orbits are admitted by Newtonian law. But here we are interested more in the law rather than the details of gravitational law, how to calculate, how to compute. That you will do at a much later stage in your life. We will restrict ourselves to circular orbits, obviously bound states. We also discussed at length the Galilean law of falling bodies, which is extraordinarily important, which said that the acceleration of a falling body was the same for all materials irrespective of their mass. And we formulated that principle by calling it as the equivalence principle, although this word was coined by Einstein only in the beginning of the 20th century, around 1910 or 1912 or so. And we argued that a combination of Newton's laws, that is Newton's laws of motion, plus the concept of centripetal force, plus the Keplerian orbit, plus the Galilean law of falling bodies. So let me write them down. So first we have Newton's laws of motion. So when we are making this statement, we are interested in the second and third law. We made use of both of them. The second law describes how the acceleration takes place. The third law describes the symmetry or the reciprocity between the force between A and B. They are equal to each other but in opposite directions. And we should remember that this statement is essentially a restatement of the conservation of momentum. That is very important for us. So we made use of these two. Then we made use of the concept of centripetal force. So what do we say? Irrespective of the origin of the physical force, so long as an object is moving in a circular orbit with a constant angular velocity, then it can always be written as mv squared by r. This is a kinematical statement which is specific, which is peculiar, and which is applicable only to circular orbits. That is something that we should remember. We made use of this centripetal force. The third concept that we used, or rather the fact that we used, was the Galilean law of freely falling bodies. Okay? And finally, we combined them with the laws of Kepler. So how many laws were there? 3 laws. So the first law was, of course, the planetary orbit, which we replaced by the circular orbit. Then we looked at equal areas traversing equal intervals of time. And the third one, which is very, very important, was a relation between the period and the radius of a planetary orbit, which is essentially t squared by r cubed is a constant. This is a constant in the sense that it is not a universal constant, but it is a constant only for planetary motion around the sun. That is something that we have to remember. So this is the fourth one. So we compiled all these and asked what would be the law that would be consistent with all these observed facts. All of them are facts, and we came to the conclusion that all of it could be consistently understood if I postulated that my gravitational force is nothing but minus g mm by r squared into unit vector. So let me not write that. Let me not write the minus sign either. This is a gravitational force. So what are we saying? We are saying that this is an inverse square law, and there are two masses which is denoted by capital M and small m. At this point, we should not assume that capital M stands for a larger mass and small m stands for a smaller mass. In fact, it is better to formulate the law without any such prejudice. Therefore, I will write Fg is equal to g m1 m2 by r squared. So what do I mean by that? I will place a mass m1 here. I will place a mass m2 here, m1, m2. This is the distance r, that is what I have. Now m1 pulls m2 towards itself, m2 pulls m1 towards itself, and you accommodate that by putting the right sign. That is what we did. So in other words, this great law, please remember, we did not derive this expression. We only arrived at this expression as a very logical and a very simple way of expressing known facts. A law can never be proved, it can only be verified. So this great law gm1 m2 by r squared is a culmination of all the observations due to Copernicus, Tycho Brahe, astronomers earlier, Halley, because there was also Halley's comet, and Galileo and Kepler. However, we should remember that this does not establish the law per se, because it is only a consistent description, and we need independent verification of this law. An independent verification of the law entails that we should be able to deal with bodies with arbitrary masses, and we should be able to determine this constant g, which is unknown to us. Whereas all this time, all that we made use of was that we know the distances and we know the periods. So we played around. In fact, that is the reason why I am emphasizing that this law is appealing, but it is not necessarily true. It need not be always valid. But we want to claim that Newtonian law is indeed a universal law. It's called the universal law of gravitation. Therefore, we have to do a little bit more of work. So let me go to the slide and show you what I intend to tell you. So the first slide summarizes whatever I wrote on the sheets of paper. So there is a body A with a mass A at a position vector RA, a body B with a mass B located at a point RB. So what we do is to define the vector separating A and B, RA minus RB, and then we wrote that the force exerted by A on B, that is very, very important. That is why I put the arrow. A go on B is minus g MA MB by RAB cubed into vector RAB, which is what I denoted pictorially for you on that sheet of paper. Okay. When we made use of the Galilean law, I made use of only one fact. There are two aspects of Galilean laws. One is the acceleration is independent of the mass of the falling body, and the second one is that the acceleration is independent of the height at which the body is from the earth. Okay, that is the statement that I want to make. So let us get back to the drawing board. So what do we want to say? What we want to say is, if I look at the Galilean law, there are two aspects: acceleration independent of mass. And the second one is that acceleration independent of the height. So what do I mean by saying that? So if you have the earth here, and if the body is falling down at all heights, h1, h2, so on and so forth, the acceleration is the same, which is given by g. That is what you call as the acceleration due to gravity, which is roughly 9.8 meter per second squared. So in deriving all these laws, I made only use of these facts, but Newtonian law says that acceleration cannot be independent of the distance from the attracting body. There is a 1 over r square term. If there is a 1 over r square term, so let me show that in your next sheet of paper. So I have my earth here, let us say, a body is falling. So as the body is falling, strictly speaking, as it keeps coming down, acceleration should increase. So this is a statement in principle. Statement in principle. In fact, there are many ways of formulating that. The other thing that you note is that if you drop two bodies, let us say separated by a certain distance d, Galileo would say that that would also fall down like this. So the distance d would be a constant if you made an observation, let us say from the top of a tower. Whereas according to Newtonian law, they should be both falling towards the center. Therefore, they cannot exactly be parallel with respect to each other. So Newtonian gravity gives a correction to the Galilean law. And what is it? The first one is that the acceleration should increase as the body falls down. And if two bodies start with a separation d, then the distance between them should keep on decreasing as they fall towards that, because both of them fall towards the center. This is a highly exaggerated figure. Never mind about that. So what we have to do is to see what kind of a correction Newtonian gravity gives, so that it is not so large that Galilean law will be violated. In that case, Newton's formulation of universal law of gravitation would not hold on the surface of the earth. That is very important. So let us fix that. This fixing is not a difficult thing at all. So what we have to do is to remember that I am going to write mass into acceleration. This is a freely falling body on the left hand side, and this will be g m mass of the earth divided by, now I will be a little bit more careful, I will write it as radius of the earth plus h whole square. So remember, when we speak of the distance between two bodies, we are actually having in our mind the center of the earth. It is not from the surface of the earth. And this height is from the surface of the earth. So to repeat again, so this is my h and my r is somewhere here. So let me draw a line to indicate that that radius is very large. Remember, I am speaking of height of the order of 10 meters, 20 meters, 100 meters maybe, but the radius of the earth is 6400 kilometers roughly. So we are speaking of a very large ratio. I will come to that number exactly. So this is what we have. The mass terms cancel. The gravitational mass is the same as the inertial mass. So therefore, now we are left with A, which actually depends on h. So what is the trick that we have to do? The trick that we have to employ is to note that this h is very small compared to r. So I am assuming that it is falling radially inwards, so that I don't have to worry about the so-called dot products and the vectors and things like that. It's a linear motion. So what I have to do is to remember that h by re is much less than 1. That is what I have to remember. So what we do? What we do is to write it as A equal to g me over h squared into 1 over 1 plus h by Re whole square. Since h by Re is a very, very small quantity, this is nothing but a perturbation on 1. So what do we have to do? We have to simply perform a binomial expansion or a Taylor expansion if you feel like. So let me do that calculation. So what we do is to make a binomial expansion. H by Re much, much less than 1. Let me call it as x. That is what I am calling it. Remember, h is the height from the surface of the earth, Re is the radius of the earth, and I am interested in the term 1 over Re plus h whole square. This quantity is nothing but 1 over Re squared into 1 plus h by Re squared. All that I have done is to pull the Re out, and this quantity is 1 over Re squared into 1 plus x whole square. This is the expression that I wanted. So let me open that up expression and see what it is. So I have 1 over 1 plus x whole square is equal to 1 plus 2x plus x squared. That is what I have. As I told you, I have x squared much, much less than x, much, much less than 1. Therefore, if I am interested in the leading order contribution, I can drop this term. So once I drop this term, this will be approximately equal to 1 over 1 plus 2x, and your binomial expansion essentially give me this is approximately equal to 1 minus 2x. That is what we are going to get. Therefore, we are now in a position to compute the correction coming to the gravitational force, whatever the constant. So what do we have now? My f of g is essentially g me m by Re squared into 1 minus 2 h by Re. I can write this particular expression now. That is the correction that I am going to get. Now if I ignore this particular term, this is nothing but ma. So ignore this particular term, this m cancels, and you see that my acceleration is nothing but fg by m, which is gme by r squared, which is your acceleration due to gravity. That is what we have. So essentially what we are saying is that for all practical purposes, the acceleration because of the earth is constant because the height at which the body is falling from is a very, very small correction or a perturbation to the radius of the earth. So it is not difficult to estimate what that value of x is. So even if I put h is equal to 100 meters, which is quite a large number, my radius of the earth is 6400 kilometers. So that will be 6.4 into 10 to the power of 6. Therefore you see x is really small. So what have we done? We have reconciled all aspects, freely falling law, freely falling body law, law of freely falling body with the Newtonian law. So in other words, we have established consistency with known facts. So that should give us the belief and the faith that probably Newtonian law of gravitation is the correct law. in which case we should be able to go beyond whatever we have done so far and find more experimental verifications, and in fact we should be able to predict new phenomena which we had not seen earlier, and that is exactly what Newton did. So in order to appreciate that, let us go back to this slide that I have made. So this slide shows a number which is roughly 3 into 10 to the power of minus 4, therefore it is a very, very small number. You can see that means the correction to the constant is roughly given by whatever we treat as a constant, 10 meters per second squared or 9.8 meters per second squared. The correction will be 1 part in 10,000. That is the statement that we are making, 3 parts in 10,000. Actually, the correction coming because of the non-spherical nature of the earth and because of the rotational nature of the earth. Earth is not entirely an inertial frame because it is rotating about its axis, is much larger than this. So it is not a bad approximation at all. So now we have to take stock of situation. What have we done? We have formulated a law based on known observations, but what is it that we knew? We knew the distances, we knew the periods, but we do not know the masses. When Galileo dropped masses, he knew the mass of the falling body, but for sure Galileo did not know the mass of the earth. G value is not determined, so it is an unknown constant. So what Galilean law is essentially doing is to determine mass of the earth into gravitational constant. Actually what Galilean law determines is mass of the earth into gravitational constant divided by the radius of the earth squared. But I am assuming that we know the radius of the earth. After all, people could navigate around the earth, or the great experiment of Eratosthenes sort of fixed the radius of the earth. So now if you want to go beyond this, and if we want to claim, look here, I have a universal law of gravitation with me, I better determine either the mass or G or both independently and verify that the law really holds. This was a task which was undertaken by Cavendish, and what he did was to directly determine the gravitational constant. This is one of the classic experiments in the history of physics which he performed over a period of 1 year between 97 and 98. He did a number of careful observations and he arrived at this value of G, which is a tiny, tiny number compared to, for example, the strength of the electrostatic force, which is given by E squared over 4 pi epsilon naught, so on and so forth. And we should better spend some time understanding how Cavendish determined the value of G. Historically, Cavendish did not claim that he was determining the value of the gravitational constant, but he made a more interesting claim. He claimed that he was weighing the earth. Actually, he did not even make that statement. He claimed that he was finding the density of the earth, because in the 18th century, when Cavendish was doing these experiments, people were very, very seriously interested in the density of the earth. So he wanted to measure the density of the earth. I don't know if I said radius. So Cavendish claimed that he was determining the density of the earth as if earth is a homogeneous, uniform mass distribution, which is not true. But never mind, but we can make some kind of a contact with all these concepts quite easily. But as far as we are concerned, what Cavendish really determined was the gravitational constant. A historical aside which is of interest at this point is that Cavendish did many, many experiments, but this experiment is called the Cavendish experiment, like we say Michelson-Morley experiment, because obviously this was the most celebrated. So when we say the Cavendish experiment, we always refer to the determination of capital G, the constant of gravitational force. So let us see what is it that Cavendish did. So the basic idea of Cavendish experiment is a null torque experiment. So this is a standard technique which you employ whenever you want to measure some delicate forces. There are two ways of measuring a force, so let me indicate that to you. So how to determine forces? One way is measure the acceleration. Measure the body's acceleration. Now this is a tedious process because you should be able to measure different positions at different times with very, very great accuracy. Then you have to smoothly join them, that is essentially calculate the tangent, you get the velocity, plot the velocity and again smoothly join them, and then you calculate the tangent again and you will get the acceleration, which is a tedious process and it is prone to errors. The second procedure is to actually arrest the motion by known force, and this is a very useful method. Arrest the motion by known force. So for example, suppose there is a plate here carrying a surface charge density sigma, there is a charge particle q. So this is minus and this is plus, so that it gets attracted in this direction. So what I will do is I will attach a spring here and I'll ask what is the new equilibrium position, where will it get rest. I know that F is equal to minus kx coming from the spring, and if the charge particle is at rest because of this, then I know that the force exerted by this plate which is carrying a surface charge density sigma is cancelled exactly by this, and I should be able to determine the electric field. That is the trick. So this arresting the motion is called null force. The net force is null. So this is a technique which you employ essentially by applying a counteracting force so that the acceleration is 0 and hopefully the velocity is also equal to 0, and then you determine the unknown force. When it comes to electrostatic forces, Coulomb realized that an even better way of determining the Coulomb law, the so-called 1 over r squared force, in fact that was also known to Cavendish, is through a torsion balance. And what does a torsion balance do? A torsion balance does not create a null force, but it creates a null torque. So what you do is, you have a, let us come back to this slide here, a null torque experiment. So this picture is from Wikipedia, and this is exactly the apparatus which was used by Cavendish, which I am going to use again and again. So what you have is a thin wire on which you suspend two rods, and then you make it get attracted by two other objects which will apply equal and opposite force so that there is a torque. Now because of the torsion, the whole thing swings and comes into an equilibrium position. So the torques are countermanded because of the torsion of the spring. That would be a null torque experiment, and then you find the angle of deflection. This is the technique which was employed by Coulomb, and what Cavendish did was to employ the same technique. So you can see the two masses here, the other two masses are not seen. I am going to describe this experiment in great detail, but this is the basic idea. Now I am going to amplify this concept through another figure which completely illustrates whatever I want to show. So you see what's happening here. Basically what Cavendish did was to go to the rooftop of his laboratory. I will tell you what his laboratory was in a few minutes. Then there is a thin wire that you see that is coming down, which is indicated as the torsion wire, and to that thin wire is attached a slender rod. Okay, that is the so-called darkened black line, bold black line. There is a slender rod, and it is exactly attached at the center of the slender rod. This is a uniform slender rod, and at the two ends you have two small masses m which are sitting there. So here small m refers to lighter object, big M refers to the heavier object. That is what you have. So the pink color that you see or the peach color that you see is the undisturbed position. Now in that undisturbed position, what happens is that there are two very heavy masses. In fact, the smaller masses and heavy masses were both made of lead. All of them were completely spherical. They are placed such that they are at equal distances from these two objects. So what happens? the heavier mass moves this lead towards itself. So, let me go back. The heavier mass, one heavier mass moves one of the objects in this direction. The other heavier mass applies a force in the opposite direction. Therefore, there is a net torque. But this net torque is countermanded by the torsion, which opposes by producing a countermanding torque. Therefore, there should be a net angle theta. So, this is the idea. And the distance between the heavier mass and the smaller mass is denoted by r. I will probably use the notation d. And basically, I want to find out the new equilibrium position because of the balance of these torques. This is the experiment. Now comes the experimental details, which we should pay great attention to. We should also pay great attention to the experimental numbers, because unfortunately your NCERT textbook is singularly lacking. There are no numbers associated with it, but we shall rectify that here. So what Cavendish did was he established his lab in a big shed in his estate. Cavendish was an aristocratic person, a rich person, a man of means. So he was a landed person, so he had a very, very big shed. So what he did was to convert the big shed somewhere in his fields as his laboratory. And what he did was this apparatus, which I showed earlier, he placed the whole apparatus in a thick wooden box. So if you look up references, for example, even Wikipedia, they will give you the dimension of the box. That was a very, very huge box and a thick box. The thickness itself was several feet. It was made of a wooden box. And this wooden box was itself enclosed in a shed, because Cavendish did not want any disturbance coming either from the wind or from the vibrations, which are because of the moving carts or chariots or wagons of those days. So he wanted essentially some kind of insulated environment. Today, of course, we perform very, very sophisticated experiments on so-called vibration-free tables. They were not available at that particular time, but Cavendish did a remarkable improvisation, and that is how we proceeded. In order to observe and in order not to disturb the apparatus, even your own approach may actually affect it. You will see that when I write down the numbers, and if you convert it into, for example, compare it with our own weight. So he never went anywhere near even the wooden box. He made two small holes both in the box and the shed, and he put two telescopes, and he peeped and he looked at whatever the angle or the oscillation of the torsion pendulum was at a far distance. That is something that we have to remember. You see, the so-called null experiment is an idealization, because if there is a null force, that simply means that the object has no force acting on it. It does not ensure for us that it is at rest. It can move with a uniform velocity. The slightest perturbation can give it a uniform velocity. In a similar manner, when you have a null torque experiment, a slightest perturbation can actually giving it a small angular acceleration. So although in our analysis we will treat the experiment to be null, actually there was a motion, but that period was enormously large. It was 20 minutes. So to complete one full oscillation, it was taking 20 minutes, which for all practical purposes you can ignore, because the period of observation, when you measure the angle, is over a period of, let us say, a second or a few seconds or even half a minute. Compared to that, the motion over 20 minutes was very, very small correction. That means Cavendish had taken enormous care to actually make the pivot completely frictionless, so on and so forth. That is what he had done. And the important point that we have to notice is that he exploited the most accurate possible measurement means that was available at his time, because his vernier scale, it was like a traveling microscope, so to say. Whatever microscope he had fixed had a least count of 0.1 millimeter. So that is something that we have to remember. Of course, when I say that the vernier scale had a least count of 0.1 millimeter, I should compare it with the other dimensions, and that is what I am going to come down to. And here you have the details. I do not know whether it will be visible or not. So let me write it down here so that you can see what it is. So experimental details. So you had the large lead balls. They were themselves suspended and they are not supposed to move. So the lead ball is playing the role of what? The earth. And the small balls, the small lead balls are playing the role of a falling body. That is something that we have to remember. So they had a mass of 158.04 kg. So he got a massive lead sphere of 158.04 kg made. If you look up the original paper, the number is given in the so-called grains, and it is 24,39,000 grains. So you should remember that when Cavendish did the experiment, or for that matter when even Newtonian formulated his laws, SI units or the CGS units were not used in Great Britain. What the British used is the so-called FPS unit, foot, pound and second. That is what they used. So they had inches, and since Cavendish wanted a very, very great accuracy, he chose a very, very small fraction of the pound, and that is what was called as a grain. So it was 24,39,000 grains. So grain was presumably, the weight of a small seed or some such thing. Okay, that is what they used. That is why the word grain is used. Okay, so there was a remarkable accuracy that was there. And what about the small lead balls? The small lead balls had a mass of 0.73 kg. So we have a fraction of more than 300 between. So the heavier mass is at least 158.73, something like 300 times, let us say, heavier than the lighter mass, and that is what they did. We are going to calculate moment of inertia. It is very, very important. So we have to worry about the mass of the rod. So the lead balls were suspended from very fine metallic wires. In fact, the radius of the metallic wire was probably about a few centimeters. Now the mass of the rod was actually wooden rod. So wood is much, much lighter than lead, we all know that, and that was 0.03 kilo. It is very important for us. So if I look at this rod and I put two masses and there is this string that is coming here, almost all the mass is at the edges. The mass of the rod itself can be ignored because we are speaking of 0.03 to 0.73. So we are speaking of something like 200 times or so. We can forget all about the mass of the rod when we are going to make an estimate. So that is fine. Then we have to worry about the distance between the balls. How long was the rod? So this distance, is this what I want? Yeah, this distance was 1.860 meters. Actually, it was a 6-foot rod, which is 1.860 meters. So you can imagine how big that wooden box was and how big that shed was. We are speaking of 1.860 meters. That is the distance that was placed. So probably I should not call it as D. Let me call it as L, because that is the notation that I am going to employ. The distance between the larger masses was also the same. Is that right? Except that one mass was here and another mass was also there. Is that okay? So if I bring it down here, and this distance is also the same. That is what I mean. They were on the either side of the two rods. Okay. We don't have to worry about the radius. We have to worry about the distance between this small rod and the big rod. So let me see what the distance between the small rod and the big rod is if I have it at my disposal. So that was of the order of 0.225 millimeter. Remember, I want a very large gravitational force. Therefore, the distance must be as small as possible. Otherwise, it will die very, very rapidly. Therefore, the distance was of the order of 0.225 meters. it cannot be millimeter because he certainly did not have the least count. So 0.225 meters, that is the distance that was there. This was 1.860 meters, and he was measuring the angle. That was the distance that was being looked at. Now what we have to do is to make an analysis and find out how we are going to determine the value of G. This is what we have to do. And I told you the least count of the vernier was 0.254 millimeter. So let us start making the analysis. So it's a very, very simple way of doing that. What I will do is I will write the torque. My torque is nothing but the length of the rod into the force, because what is it that I have? I have a rod of length L, the string is at the midpoint, there are two masses and they are attracting. Is that okay? So there is a perfect couple acting on the two bodies, that is the length into force. Therefore, this is nothing but L into G into the mass of the heavier lead ball, the mass of the smaller lead ball divided by d squared. That is what I have. So if you assume that it is exactly counteracted by the torsion, then what we are going to do is to write it as the torsion constant or whatever into theta. So just as I write F is equal to minus kx, where k is the spring constant, this is my torsion constant and this theta is the angle of deflection. This is the angle of deflection. You know by how much it has moved, and that is what Cavendish determined. So I know how to determine G. It's a simple algebraic exercise. So what is happening is that I am going to equate this. Therefore I am going to get G is equal to, so I should not be committing any mistake. So what am I going to get? I am going to get a k theta d squared over m L. So this is my primary expression for the gravitational constant, k theta d squared m L. So I know the angle of deflection, I know the distance, I know the heavier mass, I know the smaller mass, I know the length of the mass, but how do I know this constant? So everything boils down to determine the constant. So the question is how to determine K. The answer is simple. Remove everything. Remove the heavy mass, remove everything, and look at the natural oscillation. So what is the solution? Look at the natural oscillation of the system. So what do I have? I have this rod, there are two balls, and I give it a twist theta and ask how it oscillates. So if you give a small angle, theta is small, you know it executes a simple harmonic motion, and the period is essentially given by t equal to 2 pi root I by the unknown torsional constant k. That is what we have, which is a generalization of a point mass which is going to oscillate, and your I is essentially the moment of inertia. What is the moment of inertia of the system of two masses with a separation L? Now comes the important observation that I made, that the mass of the wooden rod was a very, very small fraction compared to the mass of these red rod, these two. So the moment of inertia can be very easily computed, and that is nothing but m L by 2 whole squared, because it is about this particular point of this, plus m into L by 2 whole squared of this. So that makes it 2m into L by 2 whole squared. This is my moment of inertia. So what I will do is I will measure the period. I know my moment of inertia, and that immediately gives me the spring constant. So if I did all these calculations, I get a very elegant expression for G, which I have exhibited in my slide here. I invite all of you people to please substitute all the expressions and convince yourselves. And what is your G given by? 2 pi squared LD squared by MT squared. Please remember, this small d is the separation between the big rod, the big ball and the small ball. Capital L is the length of the rod. This capital M is the mass of the big lead ball. The mass of the small ball gets cancelled, and then T is of course the period. So this is the great expression. So this is exactly what Cavendish did over a period of 1 year. He must have taken a whole lot of readings, and if you go to the internet and if you Google, you will find a reference to Philosophical Transactions of Royal Society of London, where you will find the detailed paper of Cavendish. And Cavendish arrived at the remarkable number, which is given by 6.74 into 10 to the power of minus 11. So indeed, he performed an extraordinarily delicate experiment determining a very, very small number. In writing this, of course, I have been completely slipshod and careless. I mean, that is deliberately done so that we spend some time on what we are writing. This is of course meaningless unless I specify the units, and the units are in SI units. So I leave it as an exercise for you people to compute what the SI units are. My force will be in terms of newtons, and Newton itself is what? Kg into meter divided by second squared. On the right hand side, you have the mass square divided by length square. So if you substitute the whole thing, you will get the value of G in newtons. So this is the experiment that he did, and you can easily see there were a large number of approximations. If Cavendish had gone too near the apparatus, assuming that he was a person of roughly, let us say, 6 feet tall, and he weighed well 70 or 80 kilos, that could have caused quite a lot of perturbation on the gravitational forces. So he was wise enough to stay probably meters and meters away, and he was looking at the force of attraction, which are separated by a fraction of a meter. It is very, very important to know that. In fact, an experiment of a very similar nature but of enormously greater accuracy is the classic experiment of decay, which was performed in 1964, who actually tried to verify that the mass term cancels in the gravitational force expression, Ma equal to Gmm, and we cancel that M, equivalence of inertial and gravitational mass. There actually decay ensured that even the mass of the earth will have no effect on the experiment. That is very, very important, because for example in the Cavendish experiment, it is assumed that the length of the strings which supported with the heavier masses and the smaller masses were exactly the same. Otherwise there will be a slight mismatch and the torque will not be in the plane, okay? And then the gravitational field of the earth would play a role. Decay was able to actually eliminate that. We don't have to get into that, but this is a really interesting experiment. So what we have to ask ourselves at this particular point is, how good was this experimental determination? By comparing it with the known values, and here in my slide I have picked up the known value, the most recent value. This was probably sometime in 2014 or so, and the number is displayed as 6.67408, and 31 are in parenthesis into 10 to the power of minus 11. So what do we find? We find that the first significant digit is completely agreeing. There are no order of magnitude errors. The absolute error is of the order of about 7%. Actually, a more careful experiment which was done by Dubois or somebody, I don't remember, almost 100 years later, increased the accuracy only by 2%. Okay, there was a 5% error compared to the real today's experiment, and you can see the relative error between the modern value, today's current value, and Cavendish value is about 1%. So, given the fact that the apparatus that was used was quite crude compared to what we use by modern standards, and compared with the fact that the least count was not so great compared to what we use today, compared with the fact that they were not completely vibration free, in spite of enclosing it there might be a gust of wind or a small whiff of wind, you see that the Cavendish experiment was indeed a great success, and very justifiably Cavendish is credited with the determination of G. Of course, there is a fantasy that we want to weigh the earth. It goes back to Archimedes, who said that when he discovered his principle of lever. You remember, which you studied in your 8th or 9th standard, he said that give me a place to stand and give me a sufficiently long rod, I can even weigh the earth for you. I can weigh anything for you. That was the Archimedes claim. Okay? So, probably people were influenced by that, and for various reasons people were interested in the mass of the earth and the density of the earth. Now, if we know the mass of the earth, the gravitational constant, we should be able to find the mass of the earth also, which I have shown in these slides, but I will write them down. So, let us write it down. What I would like you people to do is to actually substitute the real values and convince yourselves. Okay? So, now I go back to Galileo. That is what Galilean law of falling bodies. I will write mg equal to g, mass of the earth, mass of the object divided by radius of the earth squared. That is what I will write. But now I am not as powerless as I was 15 minutes earlier, not as helpless, because thanks to Cavendish, I know the gravitational constant. This m will go away, and I know the radius of the earth thanks to observations. Therefore, I can immediately determine the mass of the earth to be g Re squared divided by capital G. That is what I have. As I told you, Cavendish was not entirely interested in the mass of the earth, but he was interested in the mean density. After all, when I am writing the radius of the earth, that is also the mean radius, because after all we know that the earth is not a perfect sphere, but it is a geoid. It is flattened at the poles and slightly bulging at the equator. Therefore, this radius is only a mean. But anyway, if we ignore that, we will write this to be 4 pi by 3 r e cubed into rho, and I will put a bar on all of them. So, what does bar refer to? Bar refers to the mean value of the radius of the earth, and rho bar refers to the mean density. What density is this? The mass density of the earth. So, if you plug in all the numbers, well, people those days used to like to give the specific gravity rather than the density. And please remember, specific gravity is the ratio of the density of a material to the density of water, presumably at room temperature. So, rho of earth mean divided by rho water, let us say normal temperature pressure, turns out to be 5.448 plus or minus 0.033. This is the number that Cavendish got. Interestingly, we are told that actually Cavendish made a mistake, an algebraic numerical error. Apparently, he declared it to be 5.84 or something, or 5.448. It could be a transcription error or a numerical error. It is a very trivial error, substitution error. We are not going to penalize anybody for that, but the correct number is 5.448, which tells you that the earth is mostly solid and it is heavy. Even if it is not solid, it must be consisting of very, very heavy elements, which is what you have at the core of the earth. So, the water content is not great, although the 2/3 of the surface of the water is earth is covered by water. So, for comparison, you should remember the density or the specific gravity of iron is about 7 plus 7 point something, of lead is 11 point something. So, we have a mixture of various other elements, okay, a lot of silicon, so on and so forth. So, this is what Cavendish discovered or Cavendish measured. So, for that reason, he is famously known for weighing the earth or finding the weight of the earth for the first time. And we should also remember those days people did not make a distinction between the mass and the weight. So he said that I have weighed the earth. Today when we say weighing, we mean the mass, but he actually meant that he found mass into gravitation, m into g. That is what he discovered, but that is a slight some kind of deviation or a digression which we need not bother about. So we have come a long way now, but this is not where our calculation ends, because again I do not have any independent means of measuring the mass of the earth and verifying that the law of gravitation is correct. Strictly speaking, it should be possible. So what should I do? I should be able to look at the orbit of the moon and again determine the mass of the earth. That is what we have to do. Let us spend some time. Now, if the mass of the earth agrees with the value obtained by Cavendish or Cavendish-like experiment, where you looked at two independent masses, from the observations coming from the orbit of the moon, then our faith in gravitational law increases. What is the next thing that I should do? I should be able to look at the orbital motion of the earth around the sun, and I should be able to estimate the mass of the sun. Now of course I do not have any means of finding out the mass of the sun, but then I should be able to look at the orbital motion of various planets, and that should establish the mass of the sun. But luckily that is already established by the third law of Kepler, because that is how we got a constant. But then if I am intelligent, I should be able to combine the motion of the moon around the earth, the motion of the earth around the sun, and I should be able to establish a relation between the period of the moon around the earth given the distance between the earth and the moon, the period of the earth around the sun given the distance between the earth and the sun. So these are various way of consistency checking. If we did that, then gravitation would be established. But why should I stop at that point? I can proceed a little bit ahead. I can look at the moons of Mars, for example. I can look at the moons of Jupiter. Jupiter has a very, very large number of moons. I don't know, there are many names. I am not getting them right now. Okay? It has 12 moons or some such thing. I should be able to look at their periods. If they are circular, I will be able to use the formula that I have written. If they are highly elliptical, Mr. Newton anyway tells us that it is possible to determine, because Newton's laws gives you the correct planetary orbits. I should be able to determine various masses, and if all of them completely agreed with each other, now you see I am making prediction for the mass of Uranus or Mars or Jupiter, that would completely establish law of gravity. And there is one unexpected bonus that we are going to encounter, and that is an explanation of tides. People have always observed tides, and people have been fascinated by tides because the full moon night and the new moon night causes the tides, and any number of supernatural explanations were given. Newton observed tides are nothing but due to the difference of gravitational force of the sun or the moon at two different ends of the earth. So that is the correction that we have to compute. All these we will do in the next lecture. So my sincere advice to all of you is, please go back, work out all these things carefully. I did not plug in the numerical values, and we will wind up the study of whatever I told you all these days in the next lecture, and then go on to discuss the applications. Okay, have a good day. Bye.